The year is 2031. A salvo of ballistic missiles launches simultaneously from 3 different directions. Hypersonic glide vehicles streak across the upper atmosphere at 20 times the speed of sound. Cruise missiles hug the terrain at low altitude, radar signatures barely distinguishable from background noise. Any one of these threats alone would challenge the most sophisticated defense systems ever built. All 3 arriving together, from different vectors, at different altitudes, at different speeds, would have overwhelmed every missile defense system America has ever fielded. But on this day, something different happens. Every single incoming weapon is detected, tracked, intercepted, and destroyed before it reaches American soil. Not by luck, not by a single system, but by a layered, interconnected, artificially intelligent defense architecture that covers the entire continental United States from space to ground level. This is the Golden Dome, and today we are going to explore exactly how America is building it. Make sure to subscribe to the channel and hit that notification bell so you never miss a video like this one. Now let us begin this journey together. The Golden Dome is not a single weapon system. It is not a collection of missile batteries arranged around American cities. It is not an upgrade to existing defense infrastructure. It is something categorically new in the history of military technology, a fully integrated, multi-layer, multi-domain missile defense architecture that uses space-based sensors, ground-based interceptors, sea-based platforms, airborne systems, directed energy weapons, and artificial intelligence coordination to create a defensive shield covering the entire North American continent. The total projected cost is $175 billion, making it the most expensive defense program in American history. And the engineering challenges involved in building it make every previous defense program look straightforward by comparison. To understand why the Golden Dome is necessary and why it is so extraordinarily difficult to build, you first need to understand the threat it is designed to defeat. For most of the Cold War, America's missile defense problem was relatively straightforward in its parameters, even if the engineering solutions were not. The primary threat was Soviet intercontinental ballistic missiles following predictable parabolic trajectories through space. Detect the launch, track the trajectory, calculate the intercept point, and fire an interceptor. The physics were known, the geometry was understood. The challenge was purely one of engineering performance, building sensors sensitive enough and interceptors fast enough to execute the intercept reliably. That world is gone. Today's missile threat environment is fundamentally different and dramatically more complex. Russia and China have both deployed hypersonic glide vehicles that travel at speeds exceeding Mach 20 while maneuvering continuously, making trajectory prediction essentially impossible with conventional tracking methods. Both nations have developed fractional orbital bombardment systems that place warheads into low Earth orbit before deorbiting them onto targets, attacking from directions that existing ground-based radar systems were never designed to cover. Cruise missiles have become faster, stealthier, and more numerous. Ballistic missiles have been equipped with maneuvering re-entry vehicles and decoy systems specifically designed to defeat existing interceptors. North Korea continues expanding its ballistic missile arsenal with increasing range and sophistication. And non-state actors and smaller nations are acquiring rocket and missile capabilities that would have been exclusive to superpowers a generation ago. The Golden Dome must defeat all of these threats simultaneously, reliably, and continuously. The space layer of the Golden Dome is where the architecture begins, and it is where some of the most technically demanding engineering work is concentrated. Detecting a missile launch from space requires a constellation of satellites equipped with infrared sensors capable of detecting the heat signature of a rocket motor within seconds of ignition. Existing systems like the space-based infrared system already perform this function to a degree, but the Golden Dome requires a dramatically expanded constellation with much greater coverage density, lower orbital altitudes for improved sensitivity and tracking accuracy, and the ability to pass targeting data to interceptor systems fast enough to enable engagement during the boost phase, when the missile is still accelerating and most vulnerable to interception. The new space sensor layer being developed for Golden Dome involves hundreds of satellites in multiple orbital shells. Low Earth orbit satellites provide the high sensitivity and fine resolution needed for precise tracking, but cover any given point on Earth's surface for only minutes at a time. Medium Earth orbit satellites provide continuous coverage of broader areas with somewhat less resolution. The combination of these two layers, working together and sharing data through high-bandwidth inter-satellite communication links, creates a tracking picture of unprecedented completeness and accuracy. Every launch anywhere on Earth can be detected within seconds. Every trajectory can be calculated within minutes. And that data can be transmitted to interceptor systems anywhere in the defense architecture within the response time windows that modern threats demand. The ground-based mid-course defense system forms the backbone of the Golden Dome's intercept capability against long-range ballistic missiles. This is where the existing ground-based interceptor program, already deployed at Fort Greely in Alaska and Vandenberg Space Force Base in California, forms the foundation upon which Golden Dome builds. But the existing 44 interceptors are nowhere near sufficient for the threat environment Golden Dome must address. The program calls for a dramatic expansion of ground-based interceptor capacity, with new interceptor fields at additional locations across the continental United States, Alaska, and potentially overseas partner nation territories. Each new interceptor silo is a major construction project in its own right. The silo itself is a reinforced concrete structure designed to survive near-miss nuclear detonations, with walls thick enough and structural design sophisticated enough to maintain its integrity and launch capability, even as the ground around it is shaken by blast waves of extraordinary intensity. The interceptor missiles stored in these silos are among the most technically sophisticated rockets ever built. The ground-based interceptor carries an exoatmospheric kill vehicle, a device that does not use an explosive warhead, but instead destroys incoming missiles through the kinetic energy of a direct collision in space. Hitting a warhead traveling at several kilometers per second with a kill vehicle traveling at several kilometers per second requires guidance accuracy, measured in centimeters at ranges of thousands of kilometers. The sensors on the kill vehicle must distinguish the actual warhead from decoys that sophisticated adversaries deploy specifically to confuse interceptors. The propulsion system must be capable of executing the extreme maneuvers needed to correct for any tracking errors in the final seconds of intercept. Every component of this system operates at the absolute frontier of what current technology can achieve, and the Golden Dome program is pushing that frontier significantly further. The terminal defense layer addresses threats that survive or bypass the mid-course intercept layer. This is where systems like the Terminal High Altitude Area Defense, known as THAAD, and the Patriot Advanced Capability System operate, engaging missiles in the final phase of their flight as they descend toward their targets. The Golden Dome program dramatically expands the number and capability of terminal defense batteries, adding new interceptor types specifically designed for the hypersonic glide vehicle threat that existing terminal systems struggle to engage. Hypersonic glide vehicles are particularly challenging at the terminal phase because their high speed and continued maneuvering capability compress the engagement timeline to seconds, leaving minimal margin for the detect, track, target, and fire sequence that terminal defense systems must execute. This is where artificial intelligence becomes not just a useful enhancement, but an absolute operational necessity. No human operator can process the sensor data, evaluate the threat, select the optimal interceptor, calculate the engagement geometry, and authorize the firing decision in the time available against a hypersonic threat. The Golden Dome's battle management system uses machine learning algorithms trained on millions of simulated engagement scenarios to perform this entire sequence autonomously, presenting the human operator with a recommended action and executing it upon confirmation in timeframes measured in fractions of a second. The development of this battle management artificial intelligence is one of the most complex software engineering challenges in the entire program, requiring not just raw processing capability, but the ability to make correct decisions reliably across the full range of threat scenarios the system might face, including scenarios that were never explicitly included in the training data. The directed energy component of the Golden Dome represents the most technologically advanced and, in some respects, most revolutionary element of the architecture. High-energy laser weapons mounted on aircraft or eventually on space-based platforms offer a boost phase intercept capability that no kinetic interceptor system can match. During boost phase, the missile is moving relatively slowly. Its rocket motor is burning and creating a large infrared signature, and destroying it means the debris falls back on the launching nation rather than continuing toward the target. A high-energy laser traveling at the speed of light reaches its target instantaneously, requires no physical interceptor to be manufactured and stored, and can engage multiple targets in rapid succession, limited only by the power generation capacity of the platform carrying it. The airborne laser program was cancelled years ago due to technical and cost challenges, but advances in solid-state laser technology and power generation have brought directed energy boost phase intercept back into the realm of serious engineering possibility, and the Golden Dome program is investing heavily in accelerating that development. The integration challenge across all of these layers is where the Golden Dome's most profound engineering difficulty lies. Space sensors, ground-based interceptors, terminal defense batteries, airborne platforms, directed energy systems, and the battle management artificial intelligence that coordinates them all must function as a single unified system, despite being built by different contractors, using different communication protocols, operating on different frequency bands, and physically distributed across an area covering an entire continent plus space. The integration architecture that ties all of these elements together is itself a massive engineering program, requiring the development of common data standards, high-bandwidth secure communication networks, and software interfaces that allow systems designed independently to share information and coordinate actions in real time. The construction program supporting the ground-based elements of Golden Dome will be one of the largest military construction efforts undertaken in the United States since the Cold War. New radar installations must be built at locations around the continental perimeter, each requiring massive reinforced concrete structures housing antenna arrays of extraordinary size and sensitivity. New interceptor fields require not just the silos themselves, but the roads, power systems, communications infrastructure, maintenance facilities, and security systems that make an operational missile defense site function. Command and control centers must be built with the hardening and redundancy needed to survive the attacks they are designed to defend against. And all of this construction must be completed on a timeline, driven not by contractor convenience, but by the accelerating pace of adversary missile development. The Golden Dome is the most ambitious defense engineering program in American history. It is an attempt to solve a problem that has never been solved before, creating reliable, comprehensive protection for an entire continental nation against the full spectrum of modern missile threats. Every satellite in its sensor constellation, every interceptor in its silos, every radar antenna in its ground stations, every algorithm in its battle management system represents a piece of an answer to a question that determines whether the deterrence architecture that has kept major powers from fighting each other for 80 years remains credible in an era of hypersonic weapons, fractional orbital bombardment, and artificial intelligence-enabled warfare. This is not just a defense system. It is a statement about the future of national security, about whether defensive technology can keep pace with offensive innovation, and about the lengths to which a nation will go to protect its people from the most destructive weapons ever created. The engineering challenges are enormous, the cost is staggering, the timeline is demanding. But the alternative, an America vulnerable to missile attack from multiple directions simultaneously, with no credible defense, is a strategic reality that no American administration is willing to accept. And so the Golden Dome gets built. Thank you for watching. If you enjoyed this exploration of one of the most ambitious defense engineering programs ever attempted, please give this video a like and share it with anyone who finds the frontier of military technology as fascinating as it truly is. What other extraordinary defense or engineering projects would you like us to cover next? Let us know in the comments below. See you in the next video.